there is also another way to define particles. You can define them not only so much in terms of what they look like or what they're doing, but also in how they're actually moving. In physics, we refer to that as the momentum of the particles. So you can talk about where the particle is, but you also talk about where it's going and how fast it's getting there. And remember, when you talk about mass, because mass changes the space that's in it, because it changes the space-time, it actually is important to know how fast it's going through space-time, because it can actually tell you how much it will interact and how quickly it will change the space that's around it. And so in quantum physics, we study a lot about the movement of particles, or how fast they're moving, how they're moving in relationship to other particles, how they're moving in relationship to the universe, and so forth. Now, there are three major classes of molecules in terms of how they move. You can call the molecules basically tardions, or also bradyons. It's the same thing basically, but those are any kind of particle that moves less than the speed of light in terms of speed. It's actually, some of them will be at 99.9% of the speed of light, like an electron, as it moves around the nucleus incredibly fast, but it will never actually be quite at the speed of light because it has mass. And it's theoretically impossible to accelerate a particle that has mass at the speed of light or beyond it, because mass exerts inertia. It has to work to actually bend the space-time continuum that's in it. The gravitons and the Higgs boson particle that give those properties to mass, it would actually anchor the mass to space-time and makes it harder for mass to actually move through space-time. And so anything that has mass, all the particles we talked about which have mass, including all the leptons and all the quarks and the W and Z bosons, all must actually travel less than the speed of light, and we call those stardions. Now, remember that the faster you move, the slower time will go by for you. And so it will be important to know how fast the particles are moving, because it will change that particle's experience of space and time, and also change the space that's around it. Now, some particles can actually move at the speed of light because they are actually massless, and so they can move at the speed of light. Examples of that would be gluons or gravitons or photons, which are massless bosons that can't necessarily be held by the Higgs boson particle. In other words, it's not held to space-time, it's not anchored to space-time, and therefore it can move at the speed of light. And that are the ones that mediate some of those elementary forces of physics at the speeds that are unimaginable. In fact, when you're at the speed of light, essentially no time goes by for you. So for a photon, even though for us it seems like 8 minutes have gone by since it left the sun, for a photon it literally just left the sun, because for photons time doesn't really go by in the same way it goes by for us. It's almost like it instantaneously makes the trip between the sun and here. And so what you would think of as a particle moving at the speed of light, it would still take a long time to go from one place to the other? Yes, but for an observer that's outside of that, for an observer at the reference point of the particle itself, that particle is moving so fast that no time is basically going by for that particle in relationship to our time. Now, what if you had a particle that could actually move faster than the speed of light? A particle that could go so fast that could catch up with itself or with its own light. A particle that, if you were to accelerate this particle in a circle, it would actually reach the beginning of the circle before it even left it, because it's going faster than the speed of light. And so that particle will essentially be able to reach the future and hit the future life cone, or change the dimension of time for that particle so much that you actually start moving into the past, because you move faster than time, so you will get to time before time gets there. That's kind of like going to the future. But you also could go to the past by reversing the same period. And so while most observers are trapped in the hyperspace or the hypersurface of the present, some particles theoretically could accelerate beyond the speed of light. Now, we don't really know of any real particles that actually do that, but there might be some out there, and there are theoretical particles that we call tachyons, or any kind of particle that actually could potentially go beyond the speed of light. Now, all the particles that go at the speed of light are called luxons, or L-U-X-O-N, because lux means light, so that's how fast they're traveling. And tardy, as it sounds like, it's going less than the speed of light. Now, another interesting thing about matter is that in extreme situations, matter will actually assume what we call condensed states. States where these particles that we've been discussing are indistinguishable from each other. They're either so close or at such high energy states that it's almost impossible to differentiate between one hadron and the next, or between one quark and the next. Instead of acting like tiny little particles, each with independent functions and independent properties, all interacting to make the properties of a larger thing, At condensed states of matter, matter acts like one big unit composed of many small parts, but you can't distinguish the parts from the whole at that state. And we call that condensed matter. And there's a lot of examples of that, which includes polarons, magnons, excitons, phonons. And you don't really know what that is, but you need to know that when matter is condensed, either because of extreme pressure, or because of extreme low temperatures, or because of extreme high intensity of heat, you can actually create strange states of matter where the matter is acting so weird that it actually condenses and it acts like one big unit instead of multiple parts that compose it. And one of the biggest examples of that is actually something that's called the Bose-Einstein Condensate, which is a special state of matter where matter is moving so slowly that all the particles are so close that they act like basically one ginormous, huge particle that acts like a superconductor, because whatever happens to one end of the molecule happens to the other one of the particle as well, because all that mass is essentially one big thing. So if you affect one corner of it, you affect the whole thing just the same. And that's why particles like that will conduct things like electricity almost instantaneously across the particle. So theoretically, if you were to create a condensate like this, which is infinitely large, you can communicate over infinitely long distances almost instantaneously. And that has some interesting applications if you think about it. Think about creating some sort of cable created of condensed matter. You could potentially communicate at speeds that rival the speed of light, since that, in other words, you basically not be communicating from one point to the other, but both points will be connected through that condensed matter, will all be one thing. Of course, it takes an unprecedented amount of power to actually create something like this, so we're not even close of creating an application like that. Now that we've talked about these strange conditions of matter, it's also important to remember that there might be other particles out there that we haven't even begun to dream of yet, or to fathom, or to even try to understand them. And so this is just our beginnings of understanding what particle physics is like and how the matter actually acts like.